In this video, we will derive the interesting expression for the distance between a point and the plane. This picture pretty much tells the whole story. It's supposedly 3D, although it doesn't look very 3D. This is a point, and it's situated above this plane. Okay, note we have a normal to the plane right here. And of course, the normal could be located anywhere in the plane. But if we look from this point and we follow the normal, that's what this is doing right here. It's following the normal right back down to the plane, because you notice that the normal is at right angles to the plane. Okay, that's the definition of the normal. It's normal to the plane, therefore at right angles. Well, that's the shortest distance. And you can sort of visualize it if you were to go at any other angle. Of course, that would have to be longer. This would have to be longer, and therefore it's right along the normal to the plane. So that means we're going to use the dot product. Right, and here is the expression right up here. It is the normal dotted to B, and I'm using B as the vector from a point in the plane up to the point in question. So here we have, this is the point above the plane. And this is a point in the plane. Let's go back to our original figure and take a look at it. So here you see, this is the point we're talking about. It's the point above the plane. And this is any point in the plane. And we're calling that P0. Now the vector V would be the vector from P0 to P. So it's that dotted line right there. Now we can recall what we usually do, or what we do for trying to find a vector such as this. We draw a position vector from the origin of some coordinate system down here, and we draw this vector up to P0. So that's the origin, say, and here's the vector up to P0. Same point, we draw a vector, well, it's not going to work very well, up to P. So we have those two vectors, we subtract them. So if I call this one, I'll call this one A, if I want anything better, and I'll call this one B, then the vector we're looking at right here is going to be B minus A, or we could do it the other way. So here we are back at the equations, and you can see that vector V is indeed the vector to the point that we're trying to deal with from the, I'm trying to change colors here, sorry, yellow, from the point that's above the plane. And we can construct this vector V, and I put a P on here to signify that it's a vector between that up to that point. Technically, we constructed those position vectors and subtracted them to get VP, but of course once you look at this and you get the hang of it, you can see what's done. You just take the difference between the coordinates and construct the vector, but at least you at some point have to know what's behind it. And now we need the normal. We're going to project onto the direction of the normal, but if we have the normal, any old normal, we're going to get some magnitude greater than 1, and that's going to influence our distance. So we need the normal, the unit normal, because we only need the distance of the direction. So here we construct the unit normal. As we usually do, we take a vector, any vector in, and divide by its magnitude, and that gives us a unit vector. Then we take a dot product between the two. Here's a dot product between the vector from the plane up to the point and the unit vector, and we're going to write it like this. Now, to derive the interesting result that I talked about at the beginning, we'll put everything into, we're going to work out some of the terms. All right, so the normal we're going to write as here. The normal is with ABCs for its components. Then the magnitude of the normal would just be A squared, B squared, or C squared, and the square root of that. So here's our denominator right here. Got that done. Okay. Now we're going to take that dot product in the numerator here. We're looking at this other one. I'll change color here so we can have some kind of, okay, this is what we're going to work on now, and that's right here. So when we take that dot product, we get a times x1 minus x naught b times y1 minus y naught plus c times z1 minus z naught. Now we just multiplied through by the ABCs, and the first term is a times x1 plus b times y1 plus c times z1 minus, and now we have a times x naught plus b times y naught plus c times z naught. Now let's recall the equation for a plane. All right, it looked like this: a times x by plus cz minus, and there's usually a d here, but the terms were ax naught plus b y naught plus c z naught equals to 0. Okay, and the idea is that x naught, y naught, and z naught were in the plane, and any values x, y, z that satisfy this equation correspond to a point that is also in the plane. So because it equals 0, that's a test for it being in the plane. But you notice right here, this term was any point in the plane, any x naught, y naught, z naught in the plane, and of course that's exactly what we have right here. The initial terms were very similar, ax, by, cz, but in this case we have a point that is not in the plane. And of course, not if it were equal to 0, then that point would be in the plane. And that would make sense because the distance from the point to the plane would then be 0. But now I'm going to write this in the same way that we had for a plane. So we would have ax1 by1 plus cz1, and this was often abbreviated d, actually with a negative sign in it, so it's plus d. You've got to watch out where people put that d. And we can use the same d now that we had for the equation for the plane itself. That goes here. The other terms are very similar to what we've seen for the equation for a plane, except the x, y, and z pertain to a point that is not in the plane. So this is a pretty easy equation to use. All we need is the coordinates of the point in question, and we need the expression for the plane. Of course, a normal to the expression of the plane is built in, right? The normal for the plane would be 10I plus 16J plus 20K, because the components for the normal are right here in the first expression, in the first three terms for the equation for the plane. So we're just going to plug in here. So we have the normal sitting right here. Here was the d that goes right on the end, and here are the coordinates of the point. And then of course take the magnitude of the normal and put that in the denominator. That's it. That's the distance. If 0, 0, 0, the origin happens to be in the plane, if we're talking about that, is a point in the plane, then this will be 0. But if it's not, the term goes here. And the only thing you have to watch out for is that if you're looking at an expression for a plane and it's written like this, then whatever value is over here will have to be, you have to change the sign of it. Because the way this is written here presupposes that you've written the equation as, write it up here, ax, this is for the plane, by plus cz plus d is equal to 0. And you'll see it written both ways. I think Stewart writes it like this, and Thomas writes it like this. For example, those two textbooks differ on how they write it. So that is the expression for the distance from a point to the plane. Again, the shortest distance is in the direction of the normal, and that involves a dot product. But once you've worked through the steps, you can use the formula that's shown here.